Okay. So with regard to the scaling of the spectra, there's also in the past there has been a mechanistic model put forward, which also leads to the scaling of the spectra, and it's called the Coalescence Model. So in the Coalescence Model, which actually first has been put forward in the context of peripheral reactions, the idea was the following, is that let's say we have some process and particles come out. If two particles come out close to each other in momentum or in velocity, they can form a cluster and move together as an entity. So particles coming out close. Particles coming out close to each other in velocity space. Or momentum per nucleon. Can join together and come out as one fragment. So in this model, this model implies the scaling, which will arrive at in the thermodynamic model. So dN d3p will be proportional to dN. So this will be dnx, dn proton, d3p per nucleon to the power zx times dnn d3p to the power nx. And in this model, there's no assumption about the form of those distributions. They don't need to be thermal, any kind of distributions. If this condition of proximity is met, and in practice people assume that there is some kind of distance in momentum or velocity space, if two particles come out within that distance, there is some probability that they will join together and make a fragment, and you arrive at this kind of scaling. And then people adjust, here's just the proportionality constant. So this is called Coalescence Model. So there's no assumption on the form. On the form of dnp d3p over A, or so in the thermal model, you assume that these are of the thermal form, and then you get that scaling. But in the coalescence model, this could be anything. So thermal model implies coalescence, but the converse is not true. I mean, yields coalescence model yields results of the coalescence model. Maybe that's the yields results of the coalescence model. But the converse is not true. When the spectra are not of the thermal form, you might say, well, one option is that there is the thermal model is valid at some underlying level, but you have many sources which contribute. Those many sources, each of them yields this scaling, but if you make a superposition of many sources, you can get different shapes than exponential in energy. So of course, if you don't assume a specific form of those distributions, there is a chance that the model will work better than the thermal model. And just to show you the types of scalings that you can arrive at. So these are collisions of neon. Let me just squish it, maybe. So these are results from neon plus uranium collisions. I think the main author is Goodbrod. So you have one energy of the beam energy is 400, the other is 250. You have, in this experiment, only proton. So neutron distributions were not measured, just proton. So the deuteron, triton, helium-3, helium-4, all those distributions were obtained from just taking power of proton distributions. And you can see that in most cases, the description is, at least within 30% good. So the data points lines model. Lines model upon interpolation of proton data. Okay. Now, when discussing let's say when we look at the distribution in transverse momentum versus rapidity, and we discuss different sources. So target, projectile, central. So these lines are lines of constant contours of contours of constant yields. We deal with sources which are moving at finite velocity relative to each other. We talked about the situation with chemical spectral temperature. We're talking about the fact that the system cools as it expands. So with regard to this cooling, so of course system cools, so it sounds like it's losing energy, but energy is conserved. If temperatures drop and energy is conserved, this thermal energy has had to go somewhere. Okay. So where does this energy go? Any suggestion? If the system cools as it expands. So system, when system expands and it cools is because, actually thermal energy is lost because work is being done. And work is being done in pushing the different portions of the system away from each other, and while maintaining them at local equilibrium. And this amounts to generating collective motion within the system. So in the end, the energy is conserved, but energy, instead of being preserved in thermal motion, some of the energy goes from thermal motion to collective motion. And so what happens is that as the system expands, you arrive at a situation where you can have some local equilibrium at some temperature T. But this local equilibrium is moving at overall velocity relative to the center of the system. Finite velocity. So it means, let's say, if let's say I'm the right side of the system and there is a left side of the system. There is thermal motion all around, and this thermal motion pushes the outer layer, so pushes left to the one side and right to the other side. Then the interactions still generate an equilibrium, you re-equilibrate the system. But now this equilibrium is moving away from that equilibrium. Okay, and they are at relative velocity, finite velocity relative to each other. It's always finite, but the velocity may be organized. Velocities in a given region may be organized or may be completely random. So what is the difference? So if I have a situation like that, so let's say I have the one side, I don't know, let's say from whatever side you look, right and left. I look at velocities, and velocities here look this way, and over here they look the same way. Okay, there is no collective motion in this situation. Okay, if I cannot tell the right side from left side. Okay, but you arrive at collective motion if there is a prevalence of velocities pointing out this way on this side, and prevalence of velocities pointing that way on the left-hand side. Okay, I can go to the local, to some kind of rest frame where this distribution of velocities will look isotropic, but I must put myself to velocity, overall velocity moving this way in here, and to velocity moving that way over here. I begin to have correlation between velocities and position. Okay, so collective motion is basically correlation, but in position space. And normally, this will generally occur in, you expect this to occur when there are repeated interactions in the system and system is allowed to expand to vacuum. But again, the nuclear system is small. Mean free paths are comparable to the size of the system. You know that this kind of situation will occur if the system were very large, then you just put a system which is heated in the vacuum and the system explodes, okay, hydrodynamically. Because you have no pressure from outside, you have vacuum, inside there is pressure, and the system will explode. Nuclear system is small, mean free path is comparable to the distance across. Will it behave hydrodynamically? Maybe. No, in the end, they decide. Okay, but you need to have eyes open that this can occur. Okay, and if, for example, you look at temperatures and you have this difference between chemical and thermal and kinematic temperature, it shows you that there is a dynamics. Okay, so the energy cannot disappear, must go somewhere. So expect maybe there is collective motion. Collective motion is always there if you consider the longitudinal direction, because you start with collective motion. You have one nucleus moving this way, the other nucleus moving this way. You have correlation between position and velocity. In the end, there's a randomization, thermalization, but this motion persists. It continues to be there. And you may say, oh, this is just the remnant of the entrance channel, not a big deal. So you may say, oh, this is a trivial type of collective motion. But the motion, if you develop collective motion in transverse direction, that's not trivial, because it was, it's a new direction of motion, okay, which was generated spontaneously during the collision, during the reaction. So what could be how could you detect it, and what are the signs, okay? So let's assume that for whatever reason, the system can be characterized as a collection of localities, which each moves at some velocity, and then locally there is some temperature T. So distribution of velocities, you have distribution of collective velocities V. And those velocities will be functions of position in the system. And temperatures T, you may take them as a function of position. To the first order, you may say, okay, I will just consider one temperature. So then the distribution of particles in momentum, instead of some volume V, you will have integral over the whole volume occupied by the system. You have your standard factors, G over 2 pi cubed. And then you will have e to the mu x plus bx minus. And now the thermal distribution will be relative to some velocity at a given location. Over t. Okay. So before this v was put to 0 in the center of mass, or you put to 0 at the projectile velocity, or at the projectile frame, or target frame. If you are in a general frame, you can say, oh, I will just have different locations with different velocities. Could be projectile velocity, target velocity, center of mass, but maybe it's richer. Okay, maybe I have a distribution which includes transverse directions and transverse directions of collective velocities. Okay. So we have so we may have V is V projectile or V target, VCM. These are all pointing along the beam axis, but what about V with transverse components? Now, this assumption about having a velocity distribution will affect differently different particles. And let's look at that. So I will claim that different particles are differently affected. So let's look at just average kinetic energy for certain type of particles. Okay. I'll write this as average of P minus mxv plus mxv squared over 2mx, and then break it up as average P minus mxv squared over 2mx plus mxv squared over 2mx plus correlation term P minus mxv times V over 2mx. So let's look at this term. So this term, this is velocity, this is momentum in the local frame times local velocity, collective velocity direction. Now, if we have a local equilibrium, this P minus mxv will be randomly pointing isotrope with equal likelihood pointing in any local direction. Okay, this will be distributed locally. It will be distributed isotropically, while this will have a fixed direction for a given position. So this will average out to 0. Okay? Do you agree or not? So this represents local momentum. This is local momentum, local thermal momentum. This has fixed direction for location. This has no correlation with this, so it will average out to 0. Okay. This is the thermal kinetic energy. So this will have what value? 3½ T. This we don't know because it will depend on what distribution of velocities you have. So average energy of a particle will be, which is this P squared over 2mx, will be equal to 3½ T plus, we can take out the factor, mx over 2 average v squared, which will depend on whatever, it may be 0, it may be something. One thing this result tells you is that in whatever frame you look, and you look at energies, average energies of particles in that frame, the energy will depend on mass of the particle when there is a distribution of collective velocities, non-trivial, okay, when this is not 0. And the heavier the particle, the more that particle will get affected by the collective velocity. Okay? The light particle may have this small, and this will be more exposed in its kinematic characteristics. So light particles, better test thermal motion, then heavy test better the collective velocity distribution. So for if you in the model where you have constant temperature and changing velocity depending on location, you expect energy to rise linearly with mass. Well, that's a question. That's a question because if you have sources which have different density, different temperature, they will not have the same yield ratios for light and heavy. So if you have different kind of sources, you will have, maybe heavy more emitted from sources which are colder, have other velocities. So this is, that's a first try model, so to say. And the reality may be more complicated. Okay. What can also happen is that there's a history in the system. There are early stages where temperatures were higher. This will produce, more likely the light particles. And then there's the system cools, and then from late stages, the heavy particles come in. That gives you a chance that if you have your eyes open, you can unfold the history of the system by focusing on light particles, heavy particles, also different parts of spectra. So any kind of high energy tails, this will be high temperature, early stages. Low energy regions will be longer term, colder. So, there are options. This is the first try. Okay? So, but the point is that very often you want to have as simple model as possible, then run it against the data until you come to a stop and you cannot move anymore. Then you know that reality is, you have proven that the reality is more complicated. And you have motivation to improve the model. Okay? So this is the first try. Okay. Okay. So this doesn't tell you about the spectra. It's just the average energy. So maybe a model for let's try a model for spectra. So one model which people use successfully, have used successfully, it's very, it's really trivial, but, you start with trivial and see if it works. Tough luck. It's a so-called expanding shell. So you actually assume that there is one value of collective velocity, and all all that happens to this velocity is just it can take on different directions. So basically, the system. Imagine that the system is like basically shell or spherical surface which just expands. Okay, it's a very, very simple model. So it expands with one velocity which just takes different directions. So then dn d3p becomes just integral over directions of this velocity. E to the minus p minus mv squared over 2mt. Okay, and then you have your standard factors which you can add, statistical and so on. But as far as the shape of the spectra, this is it. Okay, and then you integrate over all spherical angles. So this is actually, you have d cosine theta for velocity, e to the minus p squared over 2mt. I'll drop mv squared, it's just a factor. And then you have plus m p over mt v cosine theta. That's it. Okay. Okay. So this will be e to the minus p squared over 2mt. 1, so m will cancel, t over pv e to the PV over T, e to the minus PV over T after integration. Cosine theta is the angle of between P and V. Theta is between P and V. I can choose P as the z-axis. Okay. So then dn d3p becomes equal to e to the minus p squared over 2mt hyperbolic sine of pv over t divided by p. Okay. So this changes the shape of the spectrum. People, you can make some improvement, put in the relativistic energy and so on, but that's basically what people use. And these kind of spectra are so you fit spectra fitted with P, sorry, not P, but V, T, and you can add mu. So you will have mu as before. The fact that you added the collective motion does not change yields. So yields depend only on T and mu. So only spectra. So you use V. If you are interested only in yields, you will be fitting T and mu. If you are interested in spectra, the V will be additional parameter, which will improve, hopefully improve the description of the spectrum. So in particular, just to show you results of describing data. So from the same analysis where we discussed the chemical freeze-out temperature, these are the fitted values of this velocity v in units of c. So this is Hong from 4pi. And you can see that the values are of the order, between 0.1 and 0.35 C, okay, in addition to the temperature. So this becomes sizable. These are called radial expansion velocities. So this beta here, which you see, has a subscript r. That's for this expanding shell. Okay. So velocities rise with beam energy. Eventually, they settle, even because of the v cannot go beyond c. So they settle as you go higher and higher up with energy. You may ask how much energy goes into thermal motion, how much goes into collective. So the split can be up to 50%. So this collective motion can take significant portion of overall energy that the system has. Maybe how do the spectra look? So I will first show actual theoretical results, because in theory you can switch on and off the collective motion, and then I'll show you the actual. So these are the sort of realistically computed spectra, without assuming that there is a collective motion. The collective motion just happens in a transport simulation. But it sort of shows you what you can expect. This is all in the center of mass, so kinetic energy is in the center of mass. You have pions. So pions are the lightest, so they will be least affected by collective motion. So they reflect very much the thermal characteristics. You have exponential spectra falling down with some temperature. Then you have hydrogen isotopes, protons, neutrons, tritons. So what you can see, protons have different slope. It gets flatter. It gets impacted by collective motion. Energy needs to be higher than the pionic energy, so the spectrum needs to be flatter. And then as you go to heavier and heavier particles, the spectrum gets flatter, but it also gets curved. Okay, that's a very characteristic aspect of the spectra which you find in heavy-ion collisions. The right set of the panels is actually an experimentation that you do theoretically, trying to kill the collective motion. What you do is when the system is still dense and interactions are frequent, you interchange particles' positions without changing their momenta. When you do that, you kill correlations between position and momentum, which is the characteristic of the transverse motion, and then let the system go. And when it breaks up, it all breaks up in a genuinely thermal fashion, with all spectra being exponential, parallel to each other. Okay? So no collective motion, collective motion. Okay? And to show you the real data. By the way, these lines here, these lines are fits to the transport model with this simple single shell expansion model. So you can see that the single shell fits quite reasonably something which is more complicated. And so here you have data from EOS collaboration, protons, neutrons, tritons. There are also theoretical results for comparison. And you see this, spectra which become flatter and flatter as the mass increases. And also they get curved more and more. Okay. So spectra impacted by collective expansion. Get flatter. Get when I'm saying flatter and curved, then it's a contradiction in terms. So I'm trying to find good words. So they get get softer slope. Softer slope as mass increases. With more curvature. So you could invent other velocity distributions. You know, other than this, let's say you may say, oh, this expanding shell is too trivial. So one is, the simplest distribution that you can, of velocities that you may think of is Gaussian. So let's just quickly look at what follows then. So let's say you make a distribution of collective velocities, which goes like v squared over some 2v0 squared, e to the minus p minus mv squared over 2mt. So if you convolute two Gaussians, what do you get from convolution of two Gaussians? If you convolute a Gaussian with a Gaussian, pardon? What do you get if you convolute a Gaussian with a Gaussian? Another Gaussian. You get another Gaussian. So you actually get an exponential e to the minus p squared over 2m. Let me see what I've worked out. To mt plus mv0 squared. Okay. So convolution of Gaussians yields a Gaussian. And only the width, so now the width changes with mass, okay? Or temperature changes with mass. So spectrum exponential. Effective temperature changes with mass. Okay. So if we look at those spectra, is this what the data suggests? Just pardon? Yes, that's true. But the spectra are also curved. Okay, they don't look completely thermal. Okay, so this kind of model, the model which assumes a Gaussian distribution works worse than the model which is single expanding shell. Okay, in order to explain data, the distribution of collective velocities needs to have an edge. Okay, it may be a spike. You can take a box distribution, but it needs to have an edge. A Gaussian is a too soft distribution of collective velocities to explain data. So data demand abruptly changing velocity distribution. So I'd say that this is, I don't know, let's call it the, I don't know, distribution of velocities, dp probability of velocity d3v. So a single velocity value, a delta, is good. Box distribution is good. A Gaussian, too soft. Okay. And this actually doesn't matter what energy region you go, what kind of source. The sources appear to have to be sharply changing of the velocities. Okay. Any questions? So if you use the Gaussian, then you would be, of course, there's also Coulomb here, but it's a relatively energetic collision. So if you use a Gaussian, it would behave this way. The spectrum. Comments, questions? ahead. So you can do it for the systems at those energies. If you introduce viscosity, so you can solve those systems using ideal fluid hydro. Okay, you get some results. Then you can estimate what viscosity is, what you should put in, and you put into the solution. Basically, what you find, you actually find that it's difficult to solve numerically the equations for the system of this size with the viscosity coefficients that you need to. Find that the equations are overwhelmed by this dissipated term. Basically, there's even no way to do it in any kind of satisfactory fashion, because your terms, those viscous terms, are supposed to be just a modification, and they begin to play a dominant role. You don't even know how to start solving the equations properly, because they become bigger than the terms for the ideal fluid dynamics. I mean, yes, you can do it, but it's just you have no trust in what you're getting. Even if you start the solution, then you have to stop it and go over to the expansion to the vacuum. And the results begin to depend a lot on how you stop it. So this kind of, again, something which should be just after sort of after party procedure begins to dominate your results. I mean, it's so no, you cannot do it well, hydrodynamics for these energies.
I know that in such cases it's necessary to introduce also second order.
Okay, the second order. Okay, the story is the following. So this pertains to ultra-relativistic collisions, where you put higher order terms because you face problems with causality. So if you write the regular sort of hydrodynamics with dissipative terms, following the same procedure as non-relativistically, then relativistically you find that your signals become supraluminous, and it actually becomes a problem in numerical solutions. So to stabilize those solutions, you go into the kinetic theory, and then you invoke procedures. You bring in stabilizing elements into the hydrodynamics. There is another type of hydrodynamics which has higher order terms, next order terms after viscosity and heat conduction, which is normally what is called the higher order hydrodynamics. Though that hydrodynamics, it's pleasing when you write it, write the equations down, but the equations are, by nature, they are unstable right away.
And the question R?
Pardon?
The question R, can you repeat
The question was whether one can include higher order hydrodynamics than viscosity, than the standard dissipative terms. So there are two directions. One is, I think it's Barnett equations, or they're called B somebody, which includes those higher terms. So these equations are unstable even non-relativistically. The standard hydrodynamics becomes, with dissipative terms, becomes unstable relativistically. You can cure it by going into kinetic theory and improving upon the standard. So this is a modification of the standard dissipative terms, making them basically, so the if I remember correctly, the viscosity coefficients generally may consider them as a function of frequency and wavelengths. And basically the procedure relativistically on the conservation laws. Hydrodynamics relies on conservation laws, and you just the medium just provides equation of state and or the transport coefficients. And these energies that I've discussed, where the research on equation of state is done, you're in a fortunate situation where you still know what the degrees of freedom are. You may have difficulty handling them properly, but you know what they are. So going into hydrodynamics in this energy region brings more trouble than solves problems. If you go to ultra-relativistic collisions, then the hydrodynamics gets you across those stages of the reaction where you don't know what to do. And then you know, towards the end, you turn to hadronic description. But for the duration of the system where you don't know what the degrees of freedom are or how to handle them, then you use hydrodynamics. And then it's good. So hydrodynamics is good when the system is dense and has a chance to equilibrate quickly. Then it should work okay. And these are the early stages of ultra-relativistic collisions. The change compared to the energies that I've been discussing is that you acquire many degrees of freedom because of the many new particles produced. So already if you go towards 2 GeV collisions, the number of newly created pions begins to be comparable to the number of original nucleons. And then if you go to, let's say, 10 GeV collisions, already the number of pions exceeds original nucleons by a factor of 2.5. And so, the higher you go, the more you get new degrees of freedom. So you have a chance for the system to be very dense and equilibrate quickly.